Okay, so I think we're going. And for a little bit, I'm just going to go through the archive before starting to do some actual math. And I'll probably play some music in the background just to chill out for myself. Hope it's not too loud. Hold up. Okay, I think it's probably okay to just start. So, what I'm going to do is a few things. One, let me check. I don't remember if I have it on this computer. And I don't. I need to find a Python script that I have somewhere, so I can try running something in the background while I work. So we check if it's on GitHub. And it's not, so I gotta go push it. All right, so basically we're trying to figure out if some cohomology on of some sheaves on a Herzberg surface are going to vanish. Specifically, we're looking for sheaves coming from, or at least the global sections of these sheaves are going to tell us something about linear systems on a blow up of Herzberg surface at some number of points. So, okay, so I think it's on a computer that's not plugged in then. That's no good, right? It shouldn't be too hard to make, again, so I guess we can do that. Or maybe we can just get Gemini to do it. Let's try to get Gemini to do it. So we're gonna make a program that just for a given prime p exports essentially some Macaulay 2 code that's gonna define our sheaves at the end of the day. So we're gonna just try to make that new. So it's gonna be what should we call it? Let's call it Python producer. Maybe point producer. And we're gonna ask Gemini specifically okay, so I also need to have listed this kind of thing. Alrighty, so we'll ask Gemini, given an integer n, greater than 0. Can you write that produces output points? So what do we want? Can you write a Python program that produces triples? No, they're going to be much more than that, right? It produces tuples. x0, x1, x2, x3, x4, x5. Tuples of integers. And the property is going to be that the tuples satisfy these equations. So I'm just going to copy them down. Actually, there's something that I was kind of wondering about too, which is that we're going to try to replace these equations at the end of the day with some more general ones. So right now this is on a Herzberg surface F2. And we eventually want to be able to do this for Herzberg surface like FM for general M. Maybe we do the just F2 case first. I don't think it would be too much more challenging to just start it out. Which one's the Gemini? So I think this should be not so bad, honestly. And I'm pretty sure that if we explain to it what these equations are, then actually I could just write this. I might just write this. I don't want to say. So let's see if it. Let's see if it does this. I don't know if it will be able to do it from just that information. So maybe we just start trying to write this function ourselves. So kind of don't remember the input from Python versus Julia. So we're going to do point producer. Regular? I don't know. Point producer original, and then we'll have to do Herzberg surface version with the Segre embedding taken into account. What do you write instead of end? Just return. Okay, so this should return solutions x0, x1, y0, y1, y2. Solving the equation. I think it's to the M. I could probably just figure that out. think it's to the m, and then the y's are not. Okie doke. Okay, so let's see. I kind of want to just cancel this. This produced a bunch of fucking code, but it doesn't have to be this complicated, so I'm just not going to use this. I think it's because, I mean, basically they don't know. Gemini doesn't know whether or not or how to get this system of equations, so we should be able to do everything here without needing to do that. So first of all, we can assume that y0 is not going to be 0, I think. And then we could solve for y1. Is there a better way to do this? So yeah, basically we want to produce random values. And how many do we need? Should produce, let's do t many values. So we're gonna do for I range t. We want to we're going to produce a list, I guess. List of points. And for I in this range, how are we going to do this? So we're going to first generate a random integer. So y, it's going to be random.randint. Can we do rand range? So it's going to go from 1 to let's do this. So this is going to be y0 y2 can be literally anything. Okay, so let's just write it down like this at the moment. So random.randRange n y2 we'll also do x's. And now what? So I don't think I need all of these. So for example, y2 can be anything, but y1 cannot be anything. So for a point to satisfy this equation, I need y1 to be determined. So y1 is exactly what? It's going to be x1 to the m times y0, and then times the inverse of x0 to the m. So pow x0, and then the exponent, which is going to be minus m, and then mod n. Modulo n. And then technically n should be prime here, so I'll just include it. And then it should add this point to the list, so we're going to add list of points. Dot add. I don't really remember if this is the syntax for doing this, so we're going to add a tuple. It's going to be x0, x1, y0, y1, y2. And then we're going to return list of points. Okay. So there's some semantic thing going on here. Oh, is this not how you... Right. Okay, that was some Julia. Okay, now we have to do Segre embedding. So it's going to start with a list of points. So produces from a list of points. List of points, which solves the same equation, but with it's not so clear to me actually now. Okay, the Segre embedding. Okay, this is realized inside P1 times P2, so this is going to be embedded in P5. So it's all going to be in P5 at the end of the day. So I think Gemini can do this. So the P1 times P2 have homogeneous coordinates. X0, x1, and y0, y1, y2. Can you write a function in Python that produces from the tuple an output, which is the tuple associated to the Segre embedding. Of P1 times P2. In P5. All right, so what are they? Oh, we just have to do a double for loop. Is that it? So, we don't have to do anything too fancy then. So we just say for I and the same shit, right? So for I in range, is there like a Julia thing? Range 2. For J in range. Hey, Chacho. Cat cam. But. Yeah. Hello. Booty, booty, booty. Chacho. Chacho. Oh my god, Chacho. Sorry, gotta take a quick break to pet the cat. I'm not actually apologizing for that, though. Hey, bud. Okay, so we'll take a new list. Hey. King of the castle. Oh my god. You are a menace, Chacho. A menace. You're taking up half the screen, man. I can't even see. Okay, so what are we gonna do? We're gonna take his input and we'll just do L I and then times L J plus 2. And that's gonna be element of a new list. So this will be how are we gonna do this? I think in Julia it's pretty straightforward how you go about indexing variables. And in Python, is there a way to make variables so fast like this? So I mean, I could just do could just do x0 equals 0, x1 equals 0, x2 equals 0. This is so jank. And then, no, I don't like doing that either. How would you do this? All I'm trying to do is come up with a certain index. Oh, I could just do maybe something like this. Is this even how you access? This is how you access the order of a list. Okay, so and can I just do it's gonna go through 1, and then it's gonna go JJJ, and then it's gonna go through 2. So let's do J in range 3 and I in range 2. And then now it's gonna go J 1, 2, 3, and then it's gonna go 1, 2. Is that the order that I want it to be in? I need to compare with maybe what I had before. So, in a previous life, we used I don't know if it's going to be so easy to figure out. The Wikipedia page does indexing by J seconds, so it would have done... I don't know why I'm changing the variables for this. I have to change them somewhere because I changed them before, didn't do anything. So it would have done this. And I guess I can just do m.add this thing. And then we can just return. Okay, and then for each one of these guys, I kind of want to do nmt still. And then we call just the function here, so point producer, nmt. And we'll call this a list. And then we do a new function, which is just print statements. nmt again. And this one's just going to print a list of the corresponding points. Homogenized. Print a list of the ideals to given homogeneous points. I guess I'm commenting just for myself. So what do I want to do here? I want to do point producer. And then I just want to print out everything in this. So for statement, let's say for point, in M, I want to print a statement that will tell me that point. See, bud? So the way that I have it set up here is that I have, I'm going to add a counter, I guess. So do X. There is a way to do this, I think. It's F, right? Or maybe just I. Like this. And then we do this again. So equals. And okay. One thing that I do want to do is figure out how to normalize. So point is going to have 6 coordinates, x0 to x6. And we need to divide each of them out. So I'm going to first make just a new list. It's going to be homogenized M. Maybe normalized. What would you call this? Dehomogenized? And the way that we do it is we just divide out by the last coefficient to get that to be 1. So we're going to... Yeah, actually, this is going to add a bunch of crap, isn't it? So what I want to do here is I want to produce a tuple first. So we'll do point equals tup, and then it's going to be point dot append or add. I don't know if that one works. So apparently you can just add with overloaded plus sign. But I felt like there was a way to just do like append. We could do this. That's totally fine with me. And then I kind of don't like the comma, actually. I don't know if that's what I want after. So why don't I just do this? Point's going to be a list. We'll do point.append. And then after doing all of that, we're going to we'll put the point whole thing, tupify it. And then how many times do we have to do this? We have to do this for all of the elements that are inside the list L. So for initial point in L, for product point in L, God, how do I shift? Okay, how do I make this make sense? So for every product point in L, what we're going to do is we're going to make a point object, which takes, this should be product point, and this should be product point. And then it's going to append this at the end to M. So what am I doing here? So I'm adding, luckily this one makes sense. And this should be fine too, I think. So but this one maybe doesn't. No, that's fine. Okay. Okay, so now the dehomogenized one. So for every point in our set of Segre embedded points, what we need to do is we need to take the first 5 and divide by the last one. So we'll pick demog. It's going to be 0.6. And we will, it's going to be PAL 0.6 minus 1 n. And what we're going to do is we're going to multiply all of the first 5 by this number. So what am I doing again? So I've got a list of my Segre embedded points. I want to make a set of dehomogenized points. So for each point in there, I'm going to take some random guy in this thing. And now I need to do kind of the same fuckery, right? To get to a tuple. I could have just done a list this whole time. A list of lists would have been totally fine. So we're gonna go for I and point. Let's make a new guy. We'll just make some small list. It will be so what I'm going to do is I'm going to take point I, and we're going to multiply it by dehomog. What's this going to do? It's going to do exactly what I want. And this is going to be small list. Appended this thing. And then once I've done that, I'm going to make small list a tuple. And then I'm going to append this tuple to the dehomogenized down. Okay, and now for each point, and here, what am I going to do? So we are going to say that pi is equal to this ideal. So it's going to be x0 minus x5, blah, 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 x1 minus x5. So it's going to be xi. And now in here, what do I need? I'm just going to do x, do I minus what value is this? So this is saying that x0 is this number, so this is going to be in so it's going to be 0.I and then times x 5, and then we just have to do, yeah, we just have to do this the whole way through. So so it's not, we don't need the I. So I think I'm just gonna just manually, or do I want to? I could just make this a string, and then I could print out the whole shebang, I guess. Okay. I think for this one, it would be totally fine just to copy and paste, right? But we can do this. So what am I going to do? I want to make the statement print. I just want to make a string. So we'll make a new list of strings. And then what do we need to do? We need to print the string x I minus whatever the value of point is times x5. Right, and we just need to append this to the list of strings. And then once we have all those, we do print we'll do x, we'll do p. Now I'm going to do for I and t. It's going to be print p t. I don't know if I need the second comma here. Equals, and now I want to append the string in list of strings. So equals ideal. And then it's going to be just comma separated values of list of string. So I kind of want to just do like just put a fucking comma there. And I do this? So ideal. And I just want to put strings separated commas. Alright, I think this is really lazy, but I'm going to see if I can ask Gemini to do this. Hello, Megami. Okay. I have a list of strings. I want to print the statement. This is my list of strings. String 1, string 2. Can you write code for this? Yeah, the one thing is that, okay, sure. Oh, that's actually a good idea. Yeah, just join them. Okay, yeah. So, so what do? We do formatted. Strings is, we join them with a comma. And then we just print this formatted string list. All right. That should be good. And it doesn't like the append here because of the point. I don't think I need this comma, but let's add it anyways. Okay. Try running this. We try, the statement is points, print statement. And we'll do 2, we'll do 13, we'll do 37, which I think is prime. We'll do M is 2, and we're gonna do 9 points. Syntax error. Oh, wow. Usually it's just a REPL. I think I need to quit this also. So we'll do Python 3. I point producer. And then we need to do point print statement. And same numbers, right? So 37, 2, and 9. List object has no attribute add. Tuple index out of range. Oh, because it's indexed by 0. I don't know if I actually recompiled it. Unless it's still doing that somewhere. Tuple index out of range still. Small list dot append. Point I. So line 55. For I in point. Well, that's confusing. So I can just change this to range 6. Int object is not iterable. Sick. Where's that gonna happen at? Line 61. Okay. That makes sense. Sick. List of strings. List.append takes exactly 1 argument and 5 are given. Where is this? List.append takes exactly 1 argument and 5 are given. Yeah, I agree. This is the thing that I'm fucking up with F strings. Do I just need to put an F here? We're gonna look it up. So, how does the actual F string work? I think I could do this instead, right? So I could do like this, and then just do that. That looks kind of good. I don't know. So let's try this. Quit. Run. Oh, look at that. But it gave me a bajillion more than I wanted of the exact same string. And it was 9 that whole time. So now it just needs to change. So, oh, here's one issue. That needs to go to an I. And then the other issue is just what? Is that I'm supposed to do this like there, right? So we're gonna quit. Hit that button again. Run it. And we still got the same issue. But now it's printing at 5. It's almost even more disturbing somehow. Oh, it's because we're on I. We double indexed I and I. So this one is now just going to be a J. And this one's going to be J. Okay. Okay, we've got indexing in the first variable. P0, P1, P2, P3, P4, P5, P6, P7, P6, 8. We're going to make this +1. And let's see. So why is that giving me the same thing each time? So for each point in M, we go over a list of strings, which is going to be set to be equal at the beginning of every cycle. For I in range 6, we take the list of strings and we append on point I is the thing that I actually think is okay. And for each point, I should be printing. That actually should be here. Do I just try running it one more time? That's too many, and they're all repeats still. Alrighty. So I think Gemini could debug this hella fast, so let's see. So let's, I think that's like this. Let's see what it says. So the one thing that I think is going on, I mean, I could try debugging it also. Just turn my brain off there for a second. So one thing that could be happening is M, we should just try printing M first off. And then seeing if that, so M has a bunch of crap in it, right? So we got 1, 2, that's the same crap, same crap, same crap. Okay, so our issue at the moment is with what comes up in actually the list. So what's it say? Of course, I've taken a look at your code and found a few bugs and logical issues. Sick. Here are the main problems I identified. Point producer function. In this line, you've used this for exponentiation. Right, that is bitwise, or I do need to do that. Totally forgot about that. Oh, we didn't need to go. We need to go mod n also. That's true. That actually won't affect us, but it'll be okay. So let's make those changes first. So this should be star star. And then we're gonna go mod m. Mod n, actually. And we should probably just check import math. This shouldn't really be an issue. But, okay, I can just check that that's true by myself. What was the other one? So I needed to do that. And that. And then we do a good old mod m here, n here also. And here. Okay, and then the other things that said to fix were let's see, point producer. The list is initialized outside the main loop. That's actually a good thing. I think that's there on purpose. But let's go to check. Okay, wait, point is not supposed to be there on purpose, right? We've got M. We're going to be returning M. For each guy here, we should be clearing this list like this. And then we append a bunch of stuff, and then we append tuple M. Is that why maybe we've been getting huge tuples down there? Okay, that actually should be it then. What was the last thing? So 3-point print statements. The dehomogenization logic calculates, but this list is never used. That's true. So I kind of need that. Dehomogenized M. So for point in M, this should actually be for point in dehomogenized M. Okay. Is that everything? Yeah, okay. So I think that's everything. Try it. And I'm still printing out M here. But now we're getting a list of some finite number of points. And these are all the same. So why was that? Okay, we're gonna do a little bit of troubleshooting. And try it out again. Okay, so now M is printing as a bunch of copies of different numbers, and so is the dehomogenized M. And this time it looks pretty good. So we have 1 in the final coordinate of each of the points, and so the only thing that's confusing then is why this also I don't need to print out that x5th one. So why is printing out the same guy? So we're supposed to be doing this formatted strings equals this, and then we should be printing, right? So for each point, I want to take the coordinates, I want to format a string, and then I want to print that point. I don't need this J. I don't need this. I just want that, and then this whole thing can go here. This should be good. Fuck. Because of the J. So we'll say J is 1 here. And then we print this, and then we'll do J plus equals 1. And then we'll just do J. All right. That should do it. And it does. Okay. Feels wrong, though, that I have... That's right. All right. Okay. So now we can actually do the Macaulay too. We'll do a new text file, and it's going to be smaller prime tests. So this is effectively the thing that I need to try. Not that one. Actually, there's something in here that I wanted to check, but okay, so these are the ones that I need to still check for project with a handful of people. And we can close that, close that, close this. All right, I want to copy over here. And instead of 997, we're going to pick a smaller prime, 37. That's the prime that I used here. So these are actually going to work. And then we'll go add semicolons. And then we try to do like this first one maybe. That's gonna be the hardest one probably. This 13 might actually work, so we'll try this one. And then we'll check depth, just to be sure, sat in 12. And print that out. So we'll go M2. We'll quit this just because I want to start it in here. And now we'll just load it in. So load, what's the file call that I just wrote? So it's called smallerprimes.txt. Was it a hyphen? Oh, it's because I've got underlines in this code, or no? Yeah. So we'll go back to the point producer, and I'll change this to an underline, and this to an underline, and that to an underline. We'll quit this. Run it again. Get rid of these print statements for the next time I'm going to run this thing. And try copying it over again. So I should also add just the semicolons for next time. And then I don't need the spaces, but I guess it makes it clear to see what's happening. And technically none of these should lie on C or F, but I think that's okay because to lie on those two curves, you need to have vanishing coordinates. So we'll quit, clear for my sanity, and then we'll do load smaller primes.txt. That can't be right. Oh, the P. God dang. Okay, so the P is, for whatever reason, I didn't choose that to do that. So, final time. Load it up. And copy. And it's actually in here. Run it. Quit. Clear. M2. And load smaller primes.txt. Okay. So while that thing's going on in the background, there is one other computation that I want to do, which involves essentially trying to do the same construction, but replacing the points. So actually, it's replacing the number in the Herzberg surface, so going from like F2 to F4. And going from F2 to F4, what I think I need to do is recompute a lot of the cohomology that I need to calculate. So I could have done something even smaller than what I put in here, but there's a chance that at some point, if it gets too small, it starts becoming special and no longer generic. And so we lose some vanishing. Honestly, working mod 997 and working mod 37, I can't really see the difference in like memory that would take up on my machine. There's a Grobner basis that is being computed. Grobner. And I guess what's the relative byte size between 37 and 30 and 997? So 997, so if we're working in powers of 2, doing 2 to the 10 is 997. So you need at least 10 bytes, 10 bits to convey 997. Whereas you only need 2 to the 6th. There's a chance that it uses less memory. But the internal workings of the computer, you're not really sure. Okay. So the next thing would be to try and start writing down essentially the list of intersection numbers that you'd get in the case of a Herzberg surface for arbitrary other degree, or whatever index, whatever you want to call the size of the Fn. Yeah, okay, so all right, how am I going to do this? So I want to check F4 blowing up at, let me just get the song. Should we put on some like regular, less insane music, or should we keep on listening to the furry anime? Okay, how am I gonna do this? Okay, I need to do some actual computations on paper, I think. But everything else should be relatively the same, so this ideal is different. That's actually one thing that will be different. And this ideal and this ideal are probably going to be different too. But maybe not drastically. They might actually be the same. The ideals here. So these ideals are defining just general points on this surface. So basically this Macaulay 2 code, what's it going to do? It's going to define small field, polynomial ring over small field, and this one's 6 variables. So we'll be looking at subvarieties of P5. The ideal here is the, what's it called? The ideal for Segre embedding of a Herzberg surface, which we could write code to always produce. For a general M, I guess. And then, right, we just wrote code to do this part, which is generating random points. And the last one is that we have to figure out a certain involution on the Picard group. Which I should probably just do by hand. Okay, so the one that's really kind of an issue right now is working out ideal for Segre embedding. So let's do this. Let's take Segre embedding. Consider the vanishing locus of x0 to the m y1 minus x1 to the m y0 in p1 times p2 with homogeneous coordinates x0 x1 and y0 y1 y2 respectively. Can you give me the system of equations defining the Sagre embedding of this variety in P5. I think this should be not so bad. And then we'll just have to copy and paste. So for M, I don't know. Maybe it will be, but we'll see. For I bet you M equals a specific value wouldn't be so bad. So we're going to new file this one. And we'll do phantoms or not. .txt. And it's going to be effectively the same code up to here. And then that's going to be different. This will be, I think, the same. I just need to change the ideal. Okay, looks like it actually did it. So, of course, excellent question. Okay, so we just take some minors. Now we have to translate it to a specific equation of this thing and these coordinates. The key is to strategically group the xi and the yj terms. So they pull out these factors. Oh, now they're substituting in these guys. This is better. Oh, and then they realize that this ratio is this ratio. Do I believe that? Oh, assume that we're in an affine patch. We're x0. And we need to find an expression for the ratio using only the zij coordinates. We know that for any j. This is true. This looks more right compared to this. That doesn't look right, actually. And that doesn't really look right either. It's just 4 equations. They should all just be... I think there should be 6 equations. Maybe we just do the same question, but we replace m with 4. Let's just do that. This looks a lot more legit pretty immediately. That's probably right. There should be 6 equations though, no? Unless I'm counting some redundancies in my last. I think that these 4 are probably correct. This one looks okay too. I think if I did a restart, it might just be faster. It might have just been faster at this point to do it myself. I don't know if I could have done it this fast though. So this is roughly true. But the equations that you look for, these 3 equations seem good. Yeah. That's just the equations defining this. Maybe 4 equations. Oh, well, here's 6. Alright, I think this might actually be right, so let's see. God, I don't like seeing this either, right? This is just, I think this one and this one could be simplified down to some extent. I don't know. So let's just ask. The way that I was thinking about doing this was essentially you take the same equations that Gemini produced, so basically defining new variables z0 to z5, which are given by z0 is x0 times y0, z1 is x0 times y1. And then what you have to do is you have to take your equation that defines the homogeneous, like the by degree m1 equation, and you have to somehow figure out how to multiply that by stuff in order to get some valid equations in these new variables, in these new z variables. And I think it's not so insane, but It could be just this. But then why do I have so many equations in a previous life? Yeah, let's just try this. So we'll try we'll try this. Okay, just hold it down. I copied too much. And then I want to see if I can just minimize the set of generators for this ideal. Oh man. So reduce gens I. Prune. God damn. This Tyler, man. Okay, what else is left open? So this is the last one. And there should be one other.